Hello, people. What do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of like 14, I think. Can I see your faces, please? I'd like you guys to leave video on this because it's kind of a small class, and I need to be able to tease you when that opportunity comes. Dante Quinones, yay. Bienvenidos, mi amigo. I'm on a swing today, so you'll be seeing a lot of this. I'm on the back porch of my house in Burlington. Okay, what time is it? 9:32. 1, 2, 3, 4, 5, 6, 7, 8, 9. Niner. Let's wait a couple minutes. Seems like there should be more people, so we'll wait a couple minutes. Oh, let me tell you something. I don't see Matt Bernhardt here, but Matt Bernhardt scored today. He was looking through the PowerPoint or the notes or something, and he noticed I made a serious and stupid math mistake in one of the equations I was doing. So I corrected it, uploaded the corrections, and he got 3 bonus points for doing that. So if you find some mistakes, let me know, and I will treat you with bonus points as much as possible. So let's see, we've got Dante, we've got Noemi, we've got Celine. Celine, do you speak Spanish? Let's do this class in Spanish today. Would that be okay? No, it wouldn't because I don't speak Spanish. I only know a couple words. Tyler Montano speaks Spanish. God love him. 1, 2, 3, 4, 5, 6, 7, 8, 9. We still got 9. Let's go ahead. It's going to be recorded anyway, so anybody who's not here can catch up later. So let me pick on people here to give a hard time. That's what I do. I'm going to share with you the practice question I had that I posted. Okay, so this data is like entirely made up, but it's just data that we can talk about, just something for us to talk about. So the following data was found through a series of radioligand binding assays with rat tissue. Vascular smooth, VSM is vascular smooth muscle. So we've got 1, 2, 3, 4, 5 different smooth muscles here. And each of them has got a different KD and a Bmax. So coronary arteries that feed the heart, vascular smooth muscle to the skin. So this isn't skin itself, but the muscles that lead to, or the vessels that lead to the skin. And then we've got the vascular smooth muscle that leads to skeletal muscle, and vascular smooth muscle that leads to the brain, and the uterus, which is a smooth muscle as well. Okay, question 1. How many different receptors do we have for norepinephrine based on this experiment?
2 different receptors.
2? 2 different receptors, correct. Dante, how do you know that?
By the constant dissociation numbers.
Right, you've got
300 and 310s.
Right, so you've got 2 different KDs. Now in the real world, it would be more like 310 plus or minus 10 and 280 plus or minus 20. You know what I mean? There'd be a variation. So this data is pretty idealized. But you're right, 2 different KDs means 2 different receptors. Okay, next question. Which tissue has the most high affinity receptors for norepinephrine? How can you tell? Like not the most high affinity, but the highest number of high affinity receptors. So I can only see 3 faces, so I'm going to ask Celine Ramos what she thinks about that question.
Isn't it the vascular smooth muscle to the skin because it has a low KD value, so it has a high affinity, and then it has a higher density for the Bmax?
Exactly. So the lower number of KD is the higher affinity, the higher number in Bmax is the more receptors. Excellent. Excellent. That's my Mr. Burns impersonation. Which of the tissues is least likely to respond to norepinephrine and why? Least likely to respond to norepinephrine. And when I say why, it's like based on these numbers, not based on the physiology of the tissue. So let's see, who do I got here? Do I want to tease? Matt Gremlin, is it? Matt Gamelin. Matt Gamelin.
It's the coronary arteries, isn't it? They got a high KD and a low Bmax.
That's right. So it's got a high KD, meaning it needs a higher concentration to respond to it, and a low Bmax, meaning there aren't many receptors there, which is good because you don't know this yet, but we'll talk about how norepinephrine contracts arteries, and you never want to contract arteries to the heart. That's what we call a heart attack. Okay, excellent. Thank you very much for looking at that ahead of time. You've done a fine job. I probably will put something like that on the exam. Could you repeat the reason for one? So question one was, oh God, I just deleted it. Question one was, how many different receptors are there? So you know the number of receptors based on the different KDs. Different receptors will have different KDs for the same ligand. So there was one KD that was 10 nanomolar and one that was 300 nanomolar. So you have two different KDs, so two different receptors. That make sense, Tyler? Okay, I'll wait for this.
Yeah, thank you.
Okay, good. Any other questions about these? All right, we forge ahead. So the next question then, which is really, the first part of this lecture is really part of the last lecture, but we ran out of time. So the first thing to look at today is what do you do? Oops. Hang on, I'm sorry. I'm still not great at this whole Zoom stuff. Still working on my multimedia presentation skills. Let me do this. I want to pull up, I'm sharing with you slide 2 of today's presentation, but I also want to pull up my notes so I make sure I don't forget anything. And you won't see that, but that's okay. So another thing to keep in mind about what I'm doing now is that I'm just doing outline form now. I don't have time to write it all out for every lecture. So my notes now are just notes. They're not, it's not like I'm writing a chapter anymore. Oops. Oh, shoot. There we are. I need a bigger screen, I think. I'm just working off this laptop and I'm really struggling. That's not your problem, is it? Okay, so review, binding isotherm. So this is what we talked about last time. And by doing these binding experiments, all we're looking at is a simple bimolecular reaction of the ligand binding to the receptor. And it always gives you this kind of curve, and we can find our KD and Bmax from that. So the next question is, what do you do if you don't have a radio-labeled version of your ligand, right? Like if you're talking about norepinephrine, it's easily commercially available. You just go out and buy it. But if you just synthesized a new compound, you could send that to a company and have them label it, but that would be expensive. And you say you've already got plenty of labeled norepinephrine and you're looking at a new ligand for the norepinephrine receptor, you really don't need to relabel this new compound. All you need to do is compete the hot norepinephrine off the receptor with cold new ligand. This is called a competition assay. So basically, here's your receptor. So you're doing your binding assay like before, except instead of going at higher and higher concentrations of hot ligand, you go at one concentration of hot and you add your new ligand in cold. And because they're binding to the same receptor and the binding's non-covalent, when you wait until you get to equilibrium, you'll have an equilibrium between the cold ligand binding to the receptor and the hot binding to the receptor. So because they're binding their same receptor, they're competing for it. You go to high enough concentration of that cold, you're going to compete all of the hot off. So this is what that ends up looking like. Okay, so here is 100% bound. So that's like you haven't added any unlabeled drug. And you add higher and higher concentrations of labeled drug, and the labeled drug displaces the bound drug. And at the point where you've displaced half of that bound drug, that's your IC50, or inhibitory concentration 50. It's the concentration where you inhibit half of the binding. Now that's not directly a KD. We still want to know the binding constant of the new drug for the receptor, and and the reason why that's not the KD is you can imagine if you went to higher concentration of hot ligand, it would take more cold ligand to compete it off. So that would change the IC50. So the concentration, the IC50 concentration then is dependent on how much hot ligand you have there. So you need to find a new equation that you can take account for the concentration of the hot ligand as well as the cold ligand. And that is this guy here, the Cheng-Prusov. Can you guys see the PowerPoint? Celine, give me one of these if you can see it. You can? Can you see my cursor when I go like this? Yes? Okay. So IC50 then can be found, IC50 can be used to find the KD of the cold ligand. So this is your Cheng-Prusov, and I'm not going to derive this because we spent enough time doing that, and you saw how bad my math was. So what we're showing here is the KD of ligand 2 is equal to the IC50 of ligand 2 over concentration of ligand 1, the hot ligand, divided by the KD of ligand 1. Okay, so this is the hot ligand here, its concentration and its KD. Here's the concentration it took to displace it at that concentration of cold it took to displace it. And from this equation, then you can find out the binding constant of the cold drug to the hot drug, to the receptor. Okay, does that make sense? Yes? Dante, what's that flag behind you? Is that a flag behind you? What's that?
It's the Dominican flag.
Yes. Go DR. Okay. So competition binding. So here is another experiment where you've got 4 different, let's see, 1, 2, 3, 4 different antagonists, or 4 different things to compete. And so it's like the same concentration of hot ligand, and you're doing 4 different experiments to see what the IC50 is of these 4 different ligands. And when you look at this, you can tell which one has got the highest affinity by which one is going to displace that hot at the lowest concentration. So agonist X here, or antagonist X, displaces that hot ligand at the lowest concentration. This is like, say 5 times 10 to the minus 9. So that's 5 nanomole. That's pretty low. Okay. And then this one, the red one, Y, is like, I'm going to guess 5 times 10 to the minus 7th. So the KD of X is probably about 100 times more higher affinity than for agonist Y. Okay, so you can directly compare a number of different antagonists this way using that one hot ligand. Okay, questions? Okay. All right, so that's all we have for binding. And the binding experiments are really pretty simple. It's just, a bimolecular reaction. So now we're getting into more response pharmacology, right? So you're doing a drug because the drug's going to produce some response in that tissue. And so when we talk about dose response curves, we're not going to have a binding isotherm here. We're not going to have a mathematical model that will perfectly model it, because there are just too many variables. This is this is a classic response here where you've got drug binding to a receptor, activating a G protein, which activates an effector, which activates a second messenger, which activates a kinase. That phosphorylates a target protein. Target protein then does something else. It may be another kinase. So the chain of events is so complicated, you can't mathematically model all of it. So what we do is just determine empirically what the potency of that drug is. Okay. And in pharmacology, okay, in pharmacology, the drug effect is proportional to its concentration. So as you increase the dose of the drug, you expect to see a higher response from it, and that's our dose response curve. And it's got a maximal effect. It will always peak. If it doesn't peak, then it's not pharmacological. It's probably non-specific. And we'll talk about that. Well, I talk about that with alcohol in. Why not talk about that now? So when I say non-specific, I mean like alcohol at high dose. If you took my pharmacology of recreational drug class, I said when you go to really high concentration of alcohol, it's no longer binding to a receptor to produce effect. Now it's just dissolving in the membrane and messing up the membrane. So the whole brain stops working because the membranes are changing fluidity. Same thing with an inhalation anesthetic like ether, chloroform, halothane, something like that. It's a small molecule. It's not directly activating any receptors. It's just dissolving in the membrane. And then the membranes get more fluid and all the proteins in the membrane stop working and it shuts your brain down. So that's not pharmacological. That's more non-specific. Pharmacological means drug binds to receptor, produces effect. And so you get a really nice curve when it's like that. Now, you've probably heard about homeopathic medicines. And when I say homeopathic, I don't mean herbal. Sometimes people confuse herbal medicines with homeopathic medicines. Herbal medicines are basically pharmacological, right? They've got a whole lot of chemicals there, but typically only one of them is active, and that active chemical acts like a drug. Homeopathic, the whole idea of it, homeopathic, same pathology. So the idea of homeopathy, it came up in like, I think the late 18th or early 19th century when there was no pharmacology and people didn't really know why drugs worked or how they worked or how to cure people. They thought, well, if someone's got certain symptoms, if we give them something in a really, really low dose that causes those symptoms, their body will get more resistant to them, and then they will get over those symptoms. So they're giving you basically a toxin that's going to produce the same symptoms as the disease and get your body used to it so that your body can then overcome the disease. We know today that's not true. It doesn't work that way. And the thing about homeopathy too is they take that poison that will give those symptoms and they dilute it. And at the time, they didn't know much about molecular, what molecules were, what atoms were or anything. So in retrospect, they diluted it so much that there's nothing there anymore. It's just water. If you do the mathematical calculations on a 500 times doubling dilution, at that point, based on Avogadro's number, there's no molecules of anything there. So they're taking water and they're trying to treat people with water because the water has a memory of the toxins that used to be there. Water doesn't have memory. I'm sorry. So homeopathic, I like to stress this, homeopathic medicines don't work. They are at least not for the reason they say they do. There may be a placebo effect, but there's no real effect of homeopathic medicines. Okay, get off my high horse. So pharmacology, though, is when as you increase the dose, you increase the effect. And this is going to follow a logarithmic scale, just like the binding did, right? This looks very similar to our binding curve. The difference is we're measuring effect over here, not directly binding to the receptor. And there's a maximal effect you can get with any drug, and that is Emax. And the Emax tells you about the efficacy. And then at the dose that it takes to get you half of that Emax is the ED50. That's effective dose 50. So ED50 is your potency. And just to kind of stress this again, in this class, you get away from the idea that potency means a really strong drug. Potency means, you know, what's the concentration it takes to get your effect. And the effect may be really weak, but you know, it doesn't take much to get that weak effect. Emax is really what you think of in terms of your strongest effect. So what kind of effect can you get from that drug is your Emax, and ED50 is what concentration it takes to get that effect. So what we're going to learn here from this dose response curve is ED50 and Emax. And also, you know, I talked about this in binding too. The slope of that curve also tells you whether it's a cooperative effect or if it's a linear effect. We're only going to worry about linear effects, so don't worry too much about that. But keep in mind that the slope of that curve is important as well. Okay. So drugs can have different ED50s, you know, just like they can have different KDs and different amounts of total effect. Now in binding, you know, you always get maximum binding, Bmax. You know, you get a high enough concentration, you're going to bind all those receptors no matter what your KD is. But here in dose response, you've got this, oh my God, there's a squirrel on my tree. Get off my tree. In pharmacology here, like when that drug binds to the receptor, like how well does it fit in there? Does it fit perfectly and cause that perfect conformational change in the receptor so you get perfect activation of it? Or does it bind and it only changes it a little bit, so it's not 100% activated? Or does it bind and not change the conformation of the receptor at all? So there's a, you know, continual gradation between what we call a full agonist, one that will perfectly activate that receptor, versus an antagonist that won't activate the receptor at all. It's binding to the same site, but it's not activating the receptor. So you can see that with these three drugs here. Drug A is very potent, okay, so it's acting at a very low concentration, but its maximal effect is maybe about 60%. Okay, you can't get more than a 60% of the maximal effect with this. Drug B is a full agonist, maybe a little less potent than drug A, but you can get maximal effect with it. Okay, so if you wanted maximal effect, you would have to go with drug B, and you'd go with a higher concentration than you would with drug A, but that's fine because you're getting more effect. Now, drug C is an antagonist. You get no effect no matter what concentration you go to. So there are two possible reasons for that. One is it's an antagonist. It binds to the receptor but doesn't activate it. Two is it doesn't even bind to the receptor. You're just throwing some junk in there that doesn't do anything. So you're getting 0% efficacy, but you can't get the ED50 because there is no ED50, and you don't really know if that drug's binding to it. You need to do other experiments to make sure that it really is an antagonist. One would be a competition assay. Let me check my notes real quick to make sure I'm not leaving something out. You know how thorough I like to be. You can't see my notes. You can't see my notes. You can't see my notes. Okay, so how do you know that that antagonist really is binding to the receptor? You do a competition assay. So we've got two different kinds of antagonists. One antagonist is going to bind to the same site on the receptor as the agonist and not cause that conformational change, but is blocking the ability of the agonist to get in there and activate it. So we call that a competitive antagonist because both the antagonist and the agonist are competing for the same site. And you can imagine if you're competing for the same site, if you've got, 10 agonists and 100 antagonists, the antagonists are probably going to win. You go to any concentration of agonist, you can go to a higher concentration of antagonists until there's just more antagonists. So remember the drug is out, or the ligand is always popping on and off that receptor. So when the agonist pops off the receptor, there are way more antagonists around. So it's most likely an antagonist is going to jump on there. So that's why we call it competitive. Whichever one is in higher concentration wins. Of course, it always also depends on the KDs of the two different drugs. But in general, they're competing for the same site, so the higher concentration is going to win. Here is an example of that. This is isoproterenol, which is a beta adrenergic agonist. We'll get into this eventually. So this is just the agonist by itself, and that's its dose response curve. Okay, get up to maximal effect. You add a certain concentration of propranolol, which is an antagonist for the beta receptor, and you shift the whole curve to the right. You can still get to maximal effect, but it takes more isoproterenol to get that effect. So again, competition. You got to add more in order to beat out that amount of propranolol. You double the amount of propranolol, you shift that ED50 of the agonist to the right some more. Okay, so the key with a competitive antagonist then is it will change the apparent potency, the apparent ED50 of the agonist. All right, you can still get maximal effect, but it's going to change the potency of that agonist. Sorry, just getting comfortable here. Okay, questions about that? I can't see my chat now. Anyone chat? No? Okay. The other kind of antagonist is a non-competitive antagonist. So non-competitive antagonist will bind to a different site on the receptor, not the same site as the agonist, but it changes the conformation of the receptor, so it no longer binds the agonist and can't be activated. So basically what it's doing is removing receptors. There are fewer receptors when there's a non-competitive antagonist there. This is true of an irreversible antagonist as well. We'll talk about at least one irreversible antagonist eventually, and that's a drug that will bind to the same site on the receptor as the agonist, but bind covalently and not activate the receptor. So that's an irreversible antagonist. But anyway, basically what the non-competitive or irreversible antagonist is doing is removing receptors from the equation. So if you've got fewer receptors, you can't get maximal effect anymore. But the receptors that are there are normal receptors. They haven't been changed at all because they don't have the non-competitive antagonist bound to them. So that means you're not going to change the affinity of the agonist for the receptor, because the ones that are open and available are still, perfectly normal. But you change the maximal effect you can get with that agonist because there are fewer receptors there. So here we are, norepinephrine. See, this is the one that we'll be talking about later, phenoxybenzamine. So this is an alpha adrenergic receptor irreversible antagonist. Excuse me. So you add a certain concentration of phenoxybenzamine, you decrease the maximal effect. You add a higher concentration, you decrease the maximal effect. And theoretically, you go to high enough concentration of phenoxybenzamine, you eliminate all the receptors, and now you get no effect with the agonist at all. So your non-competitive antagonist or irreversible antagonist is going to decrease the efficacy, but not change the potency of the drug. So if you've got if we back up again, you've got this drug C that produces no effect, but you synthesized it to bind to that receptor. Your next experiment then is a competition binding assay, and you see what is the effect of your drug on the dose response of the agonist. If it does this, and most drugs will, you're decreasing the apparent potency, it's a competitive antagonist. If it does this, and it decreases the efficacy, then it is a non-competitive or irreversible antagonist. Okay, questions about that? Okay, so the next one is more confusing. I've made a bit of an animation here for the next one. So what happens when you've got a partial agonist, right? We said partial agonists can produce effect, but not 100% effect. But it's going to be competing for the exact same site as the agonist that can produce 100% effect. So what if you've got a partial agonist there? So you've got a certain amount of effect. Now you start hitting it with the full agonist. What's going to happen there? Mhm. So here's your dose response of a full agonist. Okay, you've got 100% maximal response. And there's your partial agonist. Okay, you can only get like 40% response with this partial agonist. So let's say we take, okay, so we're doing a whole nother experiment, different curve. We take like this concentration of the partial agonist, we put it in there to begin with, we find the effect. Now our experiment is, once you're at that effect level, you start adding higher and higher concentrations of the full agonist. So what happens there is, okay, this is just the partial. Now you start adding full, seems to have no effect, but you go to high enough concentration of full, now it starts to outcompete the partial, and eventually you can get to full effect, okay? So the idea is this is a competitive interaction. So when the partial agonist is at its peak down here, you're seeing only the amount of effect that you can get with that partial agonist, because the partial agonist is occupying all the receptors. When you go to higher concentration of full, eventually the full is going to outcompete the partial, and then you'll get even more effect. Okay, you get more towards the full agonist's effect until you go to high enough concentration of full agonist, and now there's no more full there than partial. So the full agonist is occupying all the receptors, and you're getting full effect. Okay, that makes sense? Because that's the complicated one. I'm getting no feedback. Oh, so what happens here is the partial agonist then will, yes, can I repeat it? Yes, I can. So let me just finish and then I'll go back over it again. So the partial agonist is decreasing the apparent potency of the full agonist, shifting it to the right. Okay, so let's back up and say that again. Okay. So here's your full agonist, right? So this is one experiment. You're just doing your dose response curve with your full agonist. Second experiment, you're doing your dose response with your partial agonist. Now you compare the two, looks like the partial agonist maybe has a higher affinity than the full agonist, right? The partial agonist affinity is here, full agonist affinity is here. So partial is a little more high affinity than the full. All right, third experiment, totally different experiment. We're going to take this much partial agonist. We're going to take this concentration of partial agonist. We add it to the experiment before we start doing our experiment. We start with that much. So right off the bat, we've got effect. Okay, it looks to be 35%. So we've got 35% without any full agonist. Now we start adding higher and higher concentrations of full agonist. And what we see is we don't see it following the full agonist curve, because in here, in this whole area here, the full and the partial are competing with each other. And the partial is higher affinity and there's more of it, so the partial agonist is winning. The full isn't occupying any receptors, so you still have the same effect. As you get into here, now the partial and full are fighting with each other, but you're still only getting this much effect because the partial is still there blocking the full. When you go to high enough concentration of full, then now more of the receptors are occupied by the full than the partial. The full produces more effect, so now you're getting more effect in that experiment. And if you go to high enough concentration of the full, you totally compete off all that partial, and so you get the full effect instead of the partial effect you get with the partial agonist. So this is why these partial agonists are often called agonist-antagonists, because in some cases they seem to act like agonists, in other cases they seem to act like antagonists. So they're kind of somewhere in the middle. Like by themselves they act as agonists, but in the presence of a full agonist, they're acting like an antagonist. So in recreational drugs, if you took that class, I talk about a morphine, an opiate drug called buprenorphine. Anyone remember this? Buprenorphine. Sublimase. No, that's not Sublimase. I never know the trade names. I only know the generic names. But what's that?
Suboxone.
What's that?
Is it Suboxone?
Excellent. That's the right answer. Okay, so it's a partial agonist at the opioid receptors. So if you're an opiate addict, right, you've got very few receptors, you've downregulated receptors, you're taking this full agonist heroin, you're over-activating them, you're getting that effect. Buprenorphine then comes in, like if you go total blocking of those receptors with naloxone, well, now you go into withdrawal. You go straight from almost dead to, climbing the walls. You go right into withdrawal. So Suboxone is like in the middle there. So it's going to activate the receptors to maybe 20 or 30% of their capacity. So you're not getting high because the Suboxone won't get you that high. But at the same time, you're not totally removing the effect because, and so you're not going into withdrawal. It puts you somewhere in the middle there. And it's also going to block heroin if you take heroin while you're taking Suboxone. Not totally though. That the thing about addicts, they're not quitters. Addicts are not quitters. So you're taking Suboxone, you got a high enough concentration of heroin, you're still going to OD. But Suboxone is a good kind of maintenance drug because you're activating the receptors, but you're not getting high from them. You're just kind of maintaining. Does that make sense? Okay. Matt Bernhard's here. Yay, Matt Bernhard. Didn't shower though, did you? It's okay, neither did I. It's all right. COVID time, you don't have to shower. Okay, any questions? That's about all I have for today. It took me like 4 or 5 hours to put this lecture together yesterday. So we're going to be going on that scale. See, the hard thing for me is like with this Zoom stuff is like normally I look my notes over for 5 minutes before class and I go up and I can BS for 1 hour and 15 minutes. And drawing on the board, writing on the board takes time, so that slows me down. Now it's like boom, boom, boom. So you're getting like basically the same amount of information, but it's coming faster because I'm not writing on the board anymore. But and also this is about as much as I can do. So everybody happy? Yes, this is yes. This is no. This is happy. Yes, okay. What else? Let's see. There's one more thing about this I want to talk about, I believe. One more thing about this kind of classic pharmacology drug interaction stuff. But that will be for next Tuesday. And then we're going to go into receptor pharmacology, which is like mechanisms of action. And if you had me for cell biology, it'll be a bit of a review because it's like a lot of the same kind of stuff. But I think it's important to review this because people forget things from one semester to the next. So we'll start that on Tuesday. It'll be easier on me because I have those notes written up already. And we will talk about that. Any questions before I close this chat? No? I'll see if I can come up with some more practice questions for the weekend for you. Yeah, I'll see if I can get something posted this weekend because it's good, getting questions like that is helpful to help you understand the topic. So I'll see if I can do that this weekend. Okay, everybody happy? I'm closing my Zoom. No questions. 3,